Another exciting set of expert TA problems are up and ready for you. There's some practice problems for this next session with the worked out solutions. There are some exciting take-home test problems to work on. And there's a set of lab activities that we've got coming up. There's one more lab that I haven't posted on there yet because we've got to get to some other stuff before we get to that one. So you'll see 3 more labs I put on past the ones that we've already done that we'll be working on here over the next few days. I want to just add a little bit more content today before we get back to playing with the toys. Just a kind of a brief discussion on current and what goes on with that, a little bit more detail about current and resistors, and from there we can start to talk about resistors and circuits in different configurations, very similar to what you saw with capacitors. We can have the resistors in circuits in series, we can have them in parallel, we can have combinations of those. But let's talk first about current and resistance and things like that. If you, say, take a chunk of wire like this, and watch what's actually happening as current flows through that. Again, what we're going to do is use the standard convention that current is moving in the direction that positive charge carriers would move if it was positive charges that were doing the moving. We'll find out a little bit later how they determined it really was electrons doing it. It's really negative charges. So the electrons move in the opposite direction that we're going to say that current moves. But basically, yeah.
Why is it that current, we still define current as flowing?
That's a convention from way, way back before they knew it was electrons. And that's the way everybody was doing it, so that's the way we stuck with it.
No, it's just a convention.
Mm-hmm. Yep, yep. So what this is, though, is it really is electrons really flowing through real materials. So hopefully you can imagine if I've got a little electron and it's trying to get through this chunk of wire, this is a real material with made up of atoms and molecules in there, and our poor little electron is entering in here and he's going to start bumping into things and have a path that may look something like this, where, yeah, over time, we're going that way. In fact, the average, what they call drift velocity, speed that that thing would be going that way, is about this. So, here's my question. How come then, I'm going to have to go out of the room to do this, I guess. So for those lights to go on, I've got to send current through them. That's how fast that current's going to move. So why is it when I flip these switches, bam, those things turn right on? If that's how fast that current's actually moving. How'd that happen?
Does it stay there?
What's that?
Does it stay there until you turn it on again?
So again, it's electrons doing the moving, right? Where are they?
Stuck in the line.
They're all through the copper wires. They're those valence electrons that get delocalized from their individual atoms. They're the ones that can move around. So they're all through there waiting to do something. So it's not like I have to wait for an electron from the switch to make it all the way to this light. They're already in there waiting. What is it that makes them move? Well, we talked about that. What can I stick a charged particle into that's going to make it accelerate? An electric field. And guess how fast electric fields move? How about 3 times 10 to the 8th meters per second? Again, we'll get to that part a little bit later too. That's the part that actually, when I flip the switch, fires an electric field through the lines. That moves really fast, like instantaneous on our scale. Those charges that are sitting there see that electric field, that's what's going to make it move. But if we actually try to track an individual one, they're actually not going that fast through there. So you can imagine, though, if this is what's really happening, that This little picture I drew is going to be different depending on what we make our wire out of. Maybe there's more collisions, maybe there's less collisions. And what gives us a measure of that is the resistance of that particular material, a resistance to the flow of that electron trying to make its way through. So different materials are going to have different characteristics related to how these charges are going to be able to get through there. If I've got some resistor, if it's an ideal resistor, it will follow Ohm's law. And again, we'll do a little lab activity to get into some more details about this, which is a relationship between the voltage that we've applied across that resistor, which is again related to the electric field we just sent through there, the resistance of the resistor itself, and then here's the current that we're going to be able to get flowing through there. So we'll play with this a little bit more. You may notice that this is a linear equation, that if I plot voltage here and current here, so I do a little experiment, I've got some resistor, I apply some voltage, measure a current, apply a different voltage, measure the current, apply another voltage, measure the current, and plot that on here. What should that plot look like if my resistor does follow Ohm's law? I plot this on the y-axis, this on the x-axis. What should that look like? That's a linear equation. What should, if everything's ideal, my y-intercept be? 0. And so let's say I do an experiment and I get this. And I do another experiment, let me switch colors, and I get this. So I swap out resistors and redo my data. So here's a different resistor. What can I tell right away qualitatively about those two resistors compared to each other? Let's call this one R2, this one R1. Oops. What can I tell and how did you tell? That's the data from R1 and the data from R2. Give it a shot.
Well, the resistance of R2 is definitely greater
Yep.
than the resistance of R1.
R2 has a larger resistance than R1, and how do you tell from the graph?
The slope is steeper.
Yeah, the slope is the resistance. And again, there's a little lab activity where you'll get to play with that. Let's see, like we did with capacitors, let's talk about some physical characteristics of resistors and some things that would influence if I've got a certain resistor. Let's see what we got around here. Give me just a second. Not finding the ones I'm looking for. Let's see if I can track them down. These are, in case you've never seen them before, these are commercial resistors. I'm trying to get set of these two. Just a second. So here's a whole bunch of them. They look like that. So there's a whole set of them. So each one of those little guys is a single resistor. And you can design different resistances for these things. So what goes into determining what the resistance is going to be as far as physical parameters if you're actually making these things? And again, you probably have some ideas. We can probably piece this together, that resistance is going to depend on some things. So here's going to be my resistor. Again, that's a resistance to the flow of the charges trying to get through there. And again, that's a measure somehow of all these collisions that are occurring. So what do you suppose, what could we change to increase resistance, do you suppose? It's going to tell us a mathematical relationship. So I'm going to send an electron through there. and figure out how am I gonna make it tougher for them to get all the way to the other end. How can I make a more resistance out of that thing? Any ideas? Nothing? This is like back in the old 8 a.m. days. So, 8 a.m. or afternoons on Fridays. Bad, right? All right, I'll spot you the easy one. If I make that longer, it's got to fight through more. So a very simple way is just make it longer. It fights through more material, that's more resistance. Two more things.
Width? Maybe?
It is. But a little bit better way to say it. Combine all that together. Oh, area. It's this cross-sectional area. So here we're going to send that current through there. The bigger the area, the easier it is for our little charges to get through. Smaller the area for a given whatever, then our resistance goes up. One more thing. Exactly. Different materials are going to behave differently. And what's a measure of that? And again, sorry for physics running out of letters in the alphabet, even when we switch to the Greek alphabet. This is the resistivity of the material. It's something you can look up, or you can do experiments and determine it, or if it's common things like copper, tungsten, you can look it up in a book. And it lists the resistivity. That's a material property that gives us an idea of just how much things are colliding in here. So here's what we can do to design resistors and things that come into play. There's one more I'm going to throw out that's actually not in this particular equation. But it's an interesting one because it relates to something I think some of you may have noticed. Maybe. We'll see. We'll test you here. So the old school incandescent light bulbs that they've been using for over 100 years, the kind that you probably still have all through your house, unless you've been doing some switching, the kind that if you could look inside, they got the little filament that's all like squiggly. Do you ever notice with those, when they tend to burn out? See if anybody's ever noticed, they tend to always burn out at a certain time, or when you do something. Anybody ever notice that?
Well, they always burn out when it's least convenient, but that's some sort of, that's some sort of more basic underlying force of nature.
What was that? You ever notice it's usually when you first turn them on? You flip the switch, they flicker and poof, out they go. Usually it's not, it's sitting there doing its thing and then all of a sudden it goes out. How many have noticed it's usually when you first turn them on? So I can see hands a little higher just so I know. Oh, so okay. So you guys can back me up on this, right?
Flip the switch, pop,
Yep.
and nothing happens.
So why is that when the bulbs go out? It actually has to do with another thing that affects the resistance that's not in that equation. And that's temperature. So think about this. If I increase temperature, is my resistance going to go up or down? I'm going to increase the temperature of this thing. And think about what resistance is really measuring. It's that interaction between my little charged particles and the atoms and molecules of the thing it's trying to get through. It's looking at all those little collisions. If I heat this up, what does it do to the molecules in here? Makes them do what? Go faster, right? What does that mean for our poor little particle trying to fight its way through? So here's a bunch of my little particles. It's really cold, so they're barely moving. Here's this guy trying to make its way through. Oh, there, I snuck through. Now we heat him up, and this guy tries to make its way through. Do you get more or less collisions? These are moving faster, you're gonna get more collisions. So if I heat this up, what happens to my resistance? It goes up. So this goes up, this goes up. Let's look back at Ohm's law.
Wait, so the temperature is not factored into the resistance?
No, not in this equation. There's a whole separate equation that looks at temperature effects. We're not gonna worry about the quantitative part of that, I just wanna get the qualitative part here. So, anyone know what this is coming out of the wall here? The big thing is it's fixed. We'll talk about where that comes from, why it's that way. It's 120 volts, and that's fixed. That's a fixed value. If this is a fixed value, if that gets bigger, what happens to that? Gets smaller. If that resistance gets smaller, what happens to that? It gets bigger, okay? So, when does your little filament in that bulb that's getting where it's thinking about giving up on you, when is it going to see the most current and why? When this is big, what's this? Small. Is that going to be small when the temperature is cool or hot? Cooler, right? So when you flick that switch, you've got a cool, temperature-wise, a cool filament. That's when it's going to see the most current. That's when it's going to, and current is real particles going through there. If you've got that filament getting kind of fragile, that's when it's going to get that big burst of current. And if it can survive that, then what? Filament heats up. Resistance goes up, current goes down. Now it's okay, as long as it can survive that first burst. And so when that filament's starting to go, that's usually when you're gonna see it go, is right when you turn it on. After that, after it heats up, changes the resistance a little bit, drops that current down, now it's all happy. That making some sense? So, if you've never noticed it before, watch that the next time when your lights goes out, see if that happens. Another quick thing I'm going to throw in, you can check in your books for some more details on this, but I want to get this in for today. That power is just the rate at which energy is delivered. So you can look at it this way. It's how much energy you're delivering over a certain time. In terms of resistors, and the voltage across them and the current running through them. We saw this kind of thing when we looked at the potential energy stored in capacitors. We had some different versions depending on whether we knew Q, V, or C. In this case, it's going to be something similar if we know VI or R. As long as we know two of those, we can figure out the power being dissipated across that resistor, either in terms of I and V, in terms of V and R, in terms of I and R. Do check in your book, because they'll show you where this all comes from. I'll give you some more details on that. What I want to do instead is spend time taking a look at this part, is how then do you figure out how much it costs you to run things when you plug them into the wall? So let's say you're going to make some toast. You stick some bread in there, and you make some toast. How much is that going to cost? It's a pretty easy process. First, let's take a look at this. I'm gonna be careful what I write here. I'm just gonna write it like this. So here's roughly what you would see. How many of you pay your own utility bills? Okay, so you probably have seen this then. This is gonna be roughly what it is, about 15 cents, and we'll list it this way, per kilowatt hour. Is the rate you get charged by the power company. What are you actually being charged for? And I'll give you roundabout hint. You're not being charged for current, that's not current. You're not being charged for voltage, that's not a voltage. What is that?
You're being charged for the energy you use.
Those are odd-looking units of energy. So you're being charged 15 cents per unit of energy, these particular units. Basically, if you look at it this way, so this is kilowatts, which the kilo, that's just times 10 to the 3. So basically, units-wise, you're talking about watts. That's hours, right? That's just units of time.
3,600
So you could always convert it if you wanted from hours to seconds. So that's watts and seconds. Well, if power, should have mentioned that the units on that are watts. That is in units on that are joules per second. So if that's joules per second times seconds, it gives you joules, that's units of energy. It's just, this is how, in the United States, they tend to show that, kilowatt hours. So if that's what you're being charged, here's how we can figure this out. Let's do a couple quick examples. Let's say you've got a light bulb, and you look on the light bulb and it says it's a 60-watt bulb. And let's run it for 1 hour and see what's it gonna cost at that rate per chunk of energy. So until you get comfortable with this is probably the best way to do these is kind of a 3-step process, is first figure out how much power are we talking about in this particular problem. In this one, it's pretty easy because it tells it to you right on the bulb. It's 60 watts, but then let's change that to kilowatts so we get these units right. Next, let's figure out how much energy we're actually using. And that's just going to be the power times how long you used it. So that's not too bad. 60 times 10 to the minus 3 kilowatts. And whatever your units are on time, at this point we'll switch them to hours. In this case it was an hour. So times 1 hour. So here's how much energy we just used. And then to get the last step, we just need to multiply the energy we use times the rate that they're charging us. And we'll get the cost. So it costs you about a penny. So one more quick example. Let's say you've got an appliance of some sort, and you find out that it's going to draw 20 amps of current. And whatever this thing is, I don't know if that's an iron or something like that, let's go $2. And what's that gonna cost? So the very first step is to figure out, again, how much power are we talking about in kilowatts? Except it doesn't tell me that directly. It doesn't say it's a 12,000 watt appliance. It says it's drawing 20 amps of current, so now what? If we plug it into the wall, that's 120 volts times our current, and then that gives us then this in watts, change that to kilowatts. That times how long we're doing this, 2 hours. Shows how much energy we used, and then that times our cost per unit of energy, and we would get a price for that. So until you get the hang of it, it's probably easiest just to do it in 3 steps like this. So any questions there? Couple more quick things, and then we'll let you play with some stuff. So it's 120 volts coming out of the outlets. Do you know what kind of current comes out of there? Later, we'll talk about why. But it's different than out of those batteries we've been using out of these kits. How many of you know that that's AC current coming out of it? And know what AC stands for?
Alternating current.
That's alternating current coming out of here. It's direct current or DC current coming out of your batteries. Again, later, we'll talk about why is it AC current coming out of here. So that comes up a little bit later.
Well, it's generally a little bit easier to produce, and it's also a lot safer, right?
Not necessarily that. There's other things that came into play. There's a key part that we have to get to later of why that's our standard coming out of here. But for now, the way that actually comes into your house is with 3 different lines. This way with my colors. You've got 3 different lines coming into your house. So for most of your circuits in your house, you've got 120 volts. How do you get that? There's a 120 volt difference between these 2. So I hook up here and here, connect that to my circuits, I've got a 120 volt difference between these 2 wires. How many of you know that you probably have an outlet somewhere in your house that's 240? Take a look at dryers, I think, have that. It's a weird looking outlet. It's like round, it's like about that big that you put the plug into. It's round, it's got like 3 weird prongy things. How many of you know what I'm talking about? Okay. If not, look around your house. You probably have one in there. How do you get 240?
Use.
Connect here and here. I've got a 240 volt difference there. And there are some appliances like dryers, anyone know what else they might have? Some ovens, I think, use that. Just need more voltage, and so that's how you can jump that up to 240. What if you need something else? Less than 120, more than 240, now what? That comes later. See these big boxy things all over the place?
Transformers?
That's what does the magic. And we'll talk about that later. That these things will change that voltage to whatever you actually need for that particular application. But that is how it's coming into your house, and how it pops out the walls. Just a couple more quick things here. Because current is like real particles going through real things. Those are collisions occurring. Unfortunately, that means current can start to heat things up. And there's a limit to how much current you can send through regular household wiring before it starts to get to be a problem. Anyone know how much current your circuits are designed to handle unless you put special wiring in? Is that familiar to anyone? It's about 20 amps. So you're going to max out at about 20 amps. So what happens if you try and plug too many things in that's going to push that current over 20 amps and burn your house down? What happens instead? Ah, yeah, so some of you know that. You got fuses that are protecting things. Let me show you how fuses work in case you've never seen this before. It's kind of cool. I'm going to have you come up around here so you can see all this. What I'm going to do is pull some fuses. Which one I've got is a power source. I've got a resistor. It's kind of old. But pretend it's worth a lot. This is really valuable. And I want to run some current through it. So I'm going to do this. I'm going to connect, make a little circuit here. So I come out of the positive terminal there. Oh, and as you guys are using these, there's two different kinds of wires. These ones with the little clippy things on it. You can just like open the jaws, stick one jaw in there, and you get a good connection. It hangs on nice and tight. If I need to connect another one to that junction right there, I can literally just grab that one and off I go. So these are okay. The other style is this one, where they've got these little plugs on the end. And these ones are kind of nice because you just poke them in like that, poke them in like that. And in this case, if I have to add another one at that junction, it's nice and easy. I just poke it in the back. So you'll get a chance to play with both of these. So okay, let me finish up the circuit. So, let's see. So here's my device. I want to send a current through it. And what I could do is just go right back to here, and now I've got a complete circuit. I've got a power source with a resistor. But I want to see what I'm measuring. I want to read the current, so I've got a little current detector here. For this to have the exact same current as that, see if you guys can figure this out. Do I want this in that circuit in series with that or in parallel with that? So what says same current, series or parallel? And it's very similar to what you do with capacitors. Let's go back to capacitors. When they were in series, what did you figure out was the same? The Q's, right? If they were in parallel, what was the same? The V's. Yeah, if they were in series, what was the same? Q's. What's current? Flowing Q's. It's the only difference. So, same thing. If I put things in parallel, or if the voltages are going to be the same, I put them in series, the current's going to be the same. So I'm going to put this in series with this guy. So from here to here, and from here back to here. And if you come around this way so you can see the little meter here, you'll see when I turn my little power on, I can start to see current. By the way, I'll show you this too. What happens on a meter like this if these are backwards?
The current is flowing in the opposite direction. So
If that happens to you, it's trying to show a negative current, but it won't, so just in case. But this is a very valuable device. I want to protect it. I want to make sure that it never has more than about 2 amps running through it. Otherwise, maybe it gets damaged. and I see, oh shoot, there's no numbers on here, and I don't know if maybe somebody did this to it before I picked it up, and I didn't notice that it's already turned on, and then I connect up, then I ruin my device. So I can protect this though if I add a fuse into that circuit. How many of you are familiar with what these basic little fuses look like? So I'll pass a couple around. It's hard to see in this light, but if you look inside there, what's in there? You see anything inside? Pass another one around here. See a little wire in there? So that wire is designed to break if it sees much more than 2 amps. This just happens to be a 2 amp fuse. And you can make fuses for different things. So when that thing sees 2 amps, this is gonna break, which is cheap, easy to replace instead of that thing breaking. But for this to work, how do I need to hook this up in that circuit? So that it sees the same current as this. Better have that in series. So whatever current is going through this is going to go through this. And if I get to a current that's too much, we'll see what happens. So I'm going to connect here. Here. So now I've got my 2 amp fuse in the circuit. If you get to where you can see that fuse, and if I get somebody to turn the lights off, we'll see what happens here. So what should happen is, and there should be enough light to still see the dial there. So I can turn this current up. So let's see, right straight up is 1.5 amps. So I can run 1.5 amps all day, no problem. That's nice and safe. It's running through here. I have no problem with my device. But my device isn't going to be happy if I put much more than 2 amps through it. So let's see what happens if I try. So I'm at 2 right now. So far so good. And I'll watch that thing as I start to go up. I'm trying to do this slow. This one will cooperate. Trying to catch it just the right spot here. See that right now? You guys can't put it there. You can come around. See anything happening? See that right there? It's really not very happy, is it? So, as I go just a little bit more, and watch what will happen to my needle here. And you get just a touch more, look, what just happened? That wire snapped. I now don't have a complete circuit, so what happened to my current? It's off even though this is still turned up. But the good thing is, this is cheap and easy to replace. I've just protected this guy. So that's what the fuses are doing in your house, what your circuit breakers are doing. The only difference between this simple fuse and an actual circuit breaker, that you just flip the switch again, those are have a design. It's a couple pieces of metal like this. They're different metals that expand at different rates of temperature. And I forget exactly how this works, but as they heat up, they'll actually separate like this. And then when you flick the switch, you put them back together again. But it's the same concept. At a certain temperature, when you start to get too much current, that goes instead of your house burning down. So either you just literally replace that, or in your basement, you probably flick a switch these days to put them back together. But that's how those things are working, and that's why they're here. Okay, you want to go ahead and turn the lights back on? So one last thing then is something again I'm going to leave to you guys to take a look at this in your book. But when we're talking about resistors and circuits, have them this way. We can have them this way. And very similar to what we did with capacitors, we can come up with an equivalent resistance. And even that process is really similar, but again, look in your book for the details on this. Here's the one thing that's different, is you're gonna do these backwards from how you did them with capacitors. It's when they're in series, we're gonna add them straight up. It's when they're in parallel that we're gonna do the inverse bit. Same idea, same thing, it's just, it's backwards from what you did before. With resistors, in series add them up, in parallel do the inversing. That actually should set you up for a few of our lab activities. Very first one, so there's 3 different ones. The very first one is kind of a simple one, just to make sure you understand what in series and in parallel means with resistors, and what it means to have a closed circuit, so that you actually do get a current to flow, and you're getting it to go through your resistors, not taking some other route. And the way we're gonna do that is we're gonna make some circuits with some of this stuff. And you're gonna make your own. I've got the supplies over there to make your own. So each table can make their own Play-Doh. And we've got the commercial stuff. I've got some 9-volt batteries here. You can use the wires from the kits, and I've got a set of LEDs here that we'll see if we can get to light up. So you'll see a little activity where we're going to be using Play-Doh. So I almost hesitate to ask this. If you're willing to admit it, how many of you have eaten this? Oh, come on, I know you have. Come on, admit it. We actually need that today. I need to have people who have eaten it. Who has eaten it?
I don't think I've ever swallowed it, but I've definitely put it in my mouth.
All right, let's try that. How many have had it in their mouth? So, those of you, all right, I better make sure. So we've had somebody at this table. Anybody back there ever had it? Okay. Uh-oh. How about this table? Any of you have eaten it or had it in your mouth? Okay, so we've got some experts at all but one table. We may have to make somebody back there. That might be a key to understanding things. Okay,